Now what I'd like to do is connect the idea of Brownian motion to diffusivity. So I would, essentially I would like to be able to figure out what is the diffusivity associated with a molecule of a particular type, so that we can use it in the, quote, diffusion equation when we have concentration gradients. So let me just point out that concentration and Brownian motion are related, right? So when we were tracking individual trajectories of particles, basically what we're imagining is that each individual trajectory is an independent experiment. Well, what is concentration, right? A concentration of something, of some species, means that we're going to put a whole bunch, like many different particles at the same location at a particular time, and we're going to keep track of each one of their trajectories all at once, and then we'll just, rather than talking about millions of different experiments, we'll just talk about on average how far they spread out, and we'll keep track of that via the concentration. So something that spreads out a lot, if I take the same number of particles and then I spread them out a lot, then later I'll have a lower concentration. There's a well-known diffusion equation. So if we're keeping track of the number of species and we have like a macroscopically large number, we can write that the rate of change of concentration is equal to the divergence of the species flux, or which you can write using Fick's law as diffusivity times the Laplacian of the concentration. In this case, I'm going to imagine doing an experiment where I initially place all of the particles at the origin. So let me call that x equals 0. And so at time equals 0, the concentration is basically a delta function centered at the origin. The solution to that equation is, to that problem is well known. In fact, that's actually the so-called Green's function formulation of the diffusion equation. And it basically involves a prefactor that involves the diffusivity times time, and then a Gaussian type spatial and temporal decay. Then what I'm going to do, so that solution is easy. What I'm going to do is view the concentration profile essentially as a probability distribution, and then try to calculate different sorts of averages, statistical averages. In particular, I'm interested in matching up to our other solution of Brownian motion, which basically required me to know what the ensemble average of R squared was. So what I'm going to do is I'm going to basically take the ensemble average of the diffusion equation, essentially subject to an R squared type weighting. So let's work out what that is. So I'll take the integral of R squared times each term. And when I do this integration, I need to do it over the full spherical coordinates. So that includes the phi and theta components, which gives a 4 pi r squared dr when I do the statistical weighting. I can sort of expand that out and sort of reverse the order of those integrals to do the time derivative second and the integral first, or on the inside. And then I'll recognize that essentially the thing on the inside of the integral is the ensemble average of R squared, or it's roughly equivalent. I can do the integral on the left hand or on the right hand side, which involved the Laplacian and didn't have any time derivatives in it in the first place. And it turns out, if you sort of work through all the math that's tucked in there, that integral turns out to be a non-dimensional number, which is equal to 6. If I then go and do the comparison between the result that we got this time using the solution to the diffusion equation with concentration, and then I compare that to our previous Brownian motion solution for the ensemble average of R squared subject to random forcing, you can match terms and you can actually come up with an explicit formula for the molecular diffusivity of a small particle subject to Brownian motion. And I'll write it this time in terms of the viscosity and diameter, which is probably the more practical way to use it. So here, d is the diameter of the impurity or molecule that's in the fluid, and mu is the viscosity or the dynamic viscosity in units of Pascal seconds.